So, does it work? Yeah. Good afternoon, everybody. First of all, I really like to thank the organizers for inviting me and giving me the opportunity to tell you something about the brain of dyscalculics. And as I've heard yesterday evening, the audience is quite diverse. We have, I think, teachers, therapists, scientists. So it's not so easy for me to make the split between to explain things very easy, but not too easy, and I try to explain it slowly and easy that you can follow, but complete also on the other hand. First, I have structured my talk in different parts. In the first one, I'm going to tell you something about our brain is calculating, how your brain calculates, how my brain calculates. And then in the second part, you hear something about neuronal development of number processing. And in the third, the main one, about the brain of dyscalculics. How does the brain calculate of people with developmental dyscalculia? And finally, I will finish my talk with a study about neuronal plasticity in developmental dyscalculia. And you already see here the abbreviation, DD, so every time you see it, developmental dyscalculia is meant by it. First of all, calculating is a demanding task for us. Just imagine if you calculate 7 plus 8, you have to know the numbers. You have to know what is the meaning of plus, so you have to add these numbers. Then maybe you calculate like this, you have 7, add 3 until you get 10, so you have to keep it in mind, calculate 8 minus 3 is 5, okay, you had 10, plus 5 is 15, so just a very simple calculation task is quite demanding. And so it's not surprising that when we look at our brain, it's not just one region that is responsible for calculation and number processing. Here on this first slide, I put it the neuronal network of number processing. And the most important thing I want to show you just at the beginning, when you're still awake. And it's this region that you saw lighting up here just before. And you heard it already this morning. It's the intraparietal sulcus, and it's assumed to be the main region for our number sense, for calculation. With the next few slides, I try to fill this network with more meaning. So look at the first study. In this study, they used functional magnetic resonance imaging. It's an imaging technique which is non-invasive and gives the opportunity to focus on brain activation, on brain function. And in this study, they have shown the participants just dots. You see it here on the right-hand side. And they differed in size, in location, as well as in the numerosity. When they just looked at the location, if the location differed, they saw that mainly these areas here in the back of our brain, in the occipital cortex, were activated. However, when we look at changes in size of the dots, we get the activation more towards the parietal area in these green regions. And finally, when the numerosity changed, we get this activation here on the right-hand side in this study, which includes the intraparietal sulcus. So coming back to our model, we can already say now that this occipital pink region here is mainly responsible for visual processing, like magnitudes, and the green one, a little bit lower, comes into play when the visual stimuli get more complex, like when we have to decode Arabic digits. And further on, back to the intraparietal sulcus, we know now that it's activated also for non-symbolic magnitude processing. With my next slide, I'd like to take you with me to Brazil in the Amazon, and there is an indigene tribe, and they have a special system for numbers. They only have words for numbers like 1, 2, 3, 4, and 5, and everything that's more than 5 is just many. And researchers went to this tribe and did some magnitude comparison tasks. They let them count different things. You see it here on this image. They used their fingers and toes to count these stones, or they made such magnitude comparisons. And the very interesting result of this study was that when they were doing experiments beyond their naming range, they were able to compare and calculate magnitudes approximately as well as you and I. However, when they were asked to calculate exactly, they failed. They were completely unable. And this is because we have two different systems in our brain for number processing. On the one hand, we have a so-called spatial system for approximation. It allows us to have a feeling for magnitudes, to decide what is more, what is less, and so on. And this system is language independent. So tasks that rely on this spatial system for approximation, these people called Munduruku were able to perform the tasks. However, on the other hand, we have a verbal system, and we use this for exact calculation. And it seems to be that words for numbers are necessary for this system. Coming back to our model here, we have here this turquoise-colored area in the brain, and this is part of this language system, of this verbal system for number processing. It's typically activated when you retrieve numerical facts, and one example is multiplication. Multiplication is not so much related to calculation, it's rather learning facts and retrieving them by heart. In addition, we have these perisylvan frontal areas, which are also part of this verbal system. Interestingly, this verbal system is only on the left hemisphere and mainly in the same areas as we use for language processing. And in the superior part of the parietal lobe, this area is more responsible for guiding the attention, working memory, and eye movement. The yellow portion here also lights up when we calculate or do these tasks, and it belongs to finger counting, decision making, again eye movement, and represents kind of task difficulty. So the more difficult the task is, the stronger you recruit this supporting area. In the next slide, I'd like to focus a little bit more on our key area, the intraparietal sulcus, and where it's meant to host our mental number line. We already heard this expression this morning and also heard some of its characteristics. For example, it's assumed that this mental number line has a certain orientation, and this has been measured by the so-called snark effect. We touched it slightly this morning, only quickly, so I explain it a little bit in more detail. On a screen there are numbers presented, and subjects are asked to press as fast and as accurate as possible with their left hand for odd numbers and with their right hand for even numbers. After that, you compare reaction times, and interestingly, you recognize that you answer faster for small numbers with your left hand and you answer faster for bigger numbers with your right hand. So it's thought that our mental number line is oriented from left to right, and it has to do something with our reading direction. So mentally, our left hand is closer to the smaller numbers. That's why we answer faster, and vice versa for our right hand. Then our mental number line has a special scaling, and we heard a lot of details about this this morning, so I will go over it very quickly. We saw this morning as well that it can be logarithmic or linear, and it depends on how familiar you are in a certain number range. For example, here, kindergartens in a number range from 0 to 100, they still show logarithmic representation, whereas first graders show a linear one. Moreover, in this study, they examined also kids with dyscalculia, and they were between the 2nd and the 4th grade, and they still showed a logarithmic representation in a number range from 0 to 1000, whereas control children already showed a linear representation. And as we heard this morning, this kind of fitting corresponds to math skills. Then I already come to my second point, where we look into the neuronal development of number processing. We also heard this morning that there seemed to be a special innate magnitude understanding, and this is just one experiment which has been used to show that already 9-month-old babies have expectations regarding the outcome of simple arithmetical problems. In this example, they showed them a puppet, and then they covered it, they added another one, and babies react surprised if there is only one puppet behind the cover if they remove it. And the second slide here, we also heard it this morning, that not just we humans have a number sense, also animals, but I have brought you a video that demonstrates this capability. In this video, we have here a monkey, and on the left-hand side there is a number of dots presented, and the monkey is asked to press the Arabic digit on the left-hand side. Just have a look. This was the first mistake. So, when I looked into the audience, I could see some astonishment in your eyes, but you were pretty quiet. When I saw this video for the first time, I was surprised or frightened as well, because I'm not that good as this monkey is, not at all. And I have chosen this video to bring it because I want to demonstrate two things. On the one hand, when you just focused on small numerosities, 1, 2, 3, 4, maybe 5, we were about at the same speed level like this monkey. And this is because these small numbers don't have to be counted, they just can be perceived immediately. And this is called subitizing, which we also heard this morning. However, when it goes to higher magnitudes, then this monkey is much better than we are, but this is just because it has been trained. And this is the second thing I wanted to show with this video, that with special training you can achieve very high skills, and not only we, but also animals. During development, a lot of steps have to be fulfilled until we reach the mathematical skills and numerical understanding we have in adulthood. And I've brought you just one model how these developmental steps could look like. This model is based on a hierarchical level, and the first one is in infancy, that we have a kind of innate core system for magnitudes, so an understanding of cardinality, and another example is subitizing we just saw before. Then during preschool, there comes this verbal system, so we have to learn to calculate 1, 2, 3, and we have to make the connections between these verbal words and to the concrete magnitudes. And further on, then in school, there comes the next system, the Arabic number system, so we have to learn the Arabic digits, and again, link these Arabic digits with the number words and the magnitudes. And finally, we develop the so-called mental number line. We develop like an automated access to it, and this enables us really quickly to decide, is the result possible, which numbers is bigger, which number follows another number, and so on. And as you can imagine, while we go through all of these steps, a lot of things happen in our brain. I have brought you two studies, and they have examined children as well as adults. Here on the left-hand side, they had to solve just an approximation task, and on the right-hand side, they had to solve addition and subtractions. And both studies show that children show their main activation here in frontal areas, also in this study, whereas in adults, when they do the same task in the scanner, they show their main activation in this study in the left intraparietal sulcus, and also in this study they show stronger parietal recruitment. So taken together, in children, they show stronger activation in frontal regions, and these rely rather on higher working memory and attentional load to solve a calculation task. And during development, there is kind of an ontogenetic shift from frontal to parietal regions. So the calculations get more automatized and are followed by functional specialization of number and magnitude processing in the brain. Coming back to our model of the neural network for number processing, we have this orange part in the frontal lobe, which corresponds to executive functions, which includes like planning, controlling, inhibition, monitoring, working memory, and attention. And in general, children activate these supporting resources stronger compared to adults. Regarding the parietal representation, I have brought you this model because it is thought that we have an image about concrete magnitudes, then we have the number word and the Arabic digit, and with increasing age and experience and during schooling, these representations overlap more and more. So we think that with increasing age, if you see 3 dots, you automatically co-activate also the representations for Arabic digits and the corresponding number words. And it's getting more and more difficult to disentangle these representations. Now coming to the third part, how does the brain look of dyscalculic people? First, I have to say that regarding research, there is much less known about dyscalculia compared to dyslexia, and this is just shown in this slide or illustrated. These columns here represent the amount of money that has been spent by the NIH, the National Institute of Health from the US, since the year 2000 in $1 million. And you can see that for dyscalculia, it's much, much less compared to dyslexia. And this really shows also the lack in research where we are right now, and the knowledge about the learning disability in calculation. However, we still have a few imaging studies. One I've brought you here. You see the typical parietal areas and frontal areas that are activated during number processing. In this task, it was an approximation task, and we examined children with and without developmental dyscalculia. And what we could show in this study is that in general, dyscalculic children do not activate different areas, so they calculate with the same regions as we do. However, they show less activation almost in the entire network. Dyscalculics are indicated in striped bars, and the black bars are the normal calculating kids. Moreover, in another study, we have tested the non-symbolic distance effect. We already heard the distance effect this morning, so I don't have to explain it anymore. Non-symbolic in this way that there were concrete magnitudes presented, and they had to decide on which side are more objects. And in most of the studies, again, the intraparietal sulcus responds specifically to this distance effect, and in red they found the activation in the IPS on the right-hand side. The interesting thing in this study is that in